So in section 7.5, we want to solve radical equations. So one of the first steps in solving these equations is isolating at least one of the radicals on one side of the equation. So if you only have one radical, obviously you're going to be able to do that. And the index of our radical here, this is a square root, the index is 2. Once we have the radical isolated, we want to raise both sides of the equation to the power which is equal to the index. Since the index is 2 here, we're going to raise both sides to the power of 2. So that eliminates the radical on the left, and I get x plus 41. And on the right, I get 36. So I solve this for x, and I get x is equal to -5. Now, whenever I've raised both sides of the equation to an even power, I have to check. The check of my solution is required if I raise both sides to an even power, because some of the solutions that I may get may not solve the actual equation. So right now, this is just a proposed solution. And I won't know if I have the actual solution until I check it. So the square root of -5 plus 41 is 6. This is actually a principal square root. So the principal square root of 36 really is 6. So this solution makes my equation true. So the solution set is the set with -5 in it. So that value does make the original equation true. All right, now in this case, I need to isolate the radical. I'm going to do that by adding x to both sides of the equation. That gives me square root of 7 minus 6x equals x. The index of the radical is still 2, so I'm going to raise both sides of the equation to the second power. And I get 7 minus 6x equals x squared. This is a quadratic equation. I'm going to put it in standard form by adding 6x to both sides, subtracting 7 from both sides. So this gives me a 0 on the left, x squared plus 6x minus 7 on the right, and I interchange the left and right sides. And I can actually solve this by factoring. X plus 7 times x minus 1 are the factors of this. So x is -7. When I said x plus 7 equal to 0, I get x is -7. Or, and let me just show that step, just in case anyone has questions about that. So the zero product principle tells me either x plus 7 is 0, which means x is -7, or x minus 1 is 0, which means x is 1. And these again are proposed solutions. I must check this because I raised both sides of the equation to an even power. So my original equation is 7 minus the square root of 7 minus 6x. So let's check negative 7. So does the square root of 7 minus 6 times negative 7 minus negative 7, does that equal 0? So this is the square root of 7 plus 42 plus 7 equals 0. So that's the square root of 49, which is 7. 7 plus 7 equals 0 is false. So this tells me that x is not negative 7. That proposed solution doesn't work. So let's check x equal to 1. Square root of 7 minus 6 times 1. Notice how I go back to the original equation. Minus x, which x is 1, needs to equal to 0. So this is the square root of 7 minus 6 minus 1. That needs to equal 0. And the square root of 1 minus 1 equals 0 is true, since the square root of 1 is 1. So 1 minus 1 equals 0 is true. So this basically tells me that my solution set, I can only accept the proposed solution of 1. So 1 does make the original equation true. So that's my solution. All right, in the next equation, I'm subtracting, in order to isolate the radical, I need to subtract 12 from both sides. So I get the principal square root of x minus 3 is equal to negative 8. And a principal square root is always going to be positive. So this then will never be true. So the solution set is the empty set. The principal square root, which is what we have when we are using the radical symbol, always has to have a positive value as its result when I'm dealing with the real numbers. So solution set is empty. Sometimes formulas involve radicals. And here I want to solve this formula. And I should have one of the variables that you want to solve for. Let's solve this for g. And notice that the formula involves a cube root. So since the index is 3, I'm going to raise both sides of the equation to the third power. The radical is already isolated. So I always raise, once I isolate the radical, I always raise both sides of the equation to the power that is the same as the index. So k cubed equals 3u over pi g. I'm going to multiply both sides of the equation by pi g. So I'll multiply the left side by pi g, and I'll multiply the right side of the equation by pi g. So that gives me pi g k cubed equals 3u, and I'm solving for g here. So I'm going to divide the left side by pi k cubed so that g will be isolated, and I have to also divide the right side by that. So now I've solved for g. G equals 3u over pi k cubed. That's my final solution. Okay, so in the final problem, I have a disguised radical written as a rational exponent. We know from our earlier work that a rational exponent is merely a radical. So this could be written as the fourth root of 2x plus 6 plus 1 equals 3. Or we could have left it as a power of 1/4. So this is also a radical equation. So I need to isolate the radical. The fourth root of 2x plus 6 equals 2. So if I raise both sides of this to the power that equals the index, which in this case that power is 4, I eliminate the radical and I get 2x plus 6 equals 16. And let's subtract 6 from both sides. And 2x equals 10, which means x has to be 5. And I just want to check, since I have raised both sides to an even power, the check is required. So 2 times 5 plus 6 to the 1/4 needs to be added to 1 and give 3. So this is 16 to the 1/4 plus 1 needs to be 3. And we know 16 to the 1/4 is the fourth root of 16, which is 2. And 2 plus 1 really does equal 3. So our solution set then is the set containing 5, since 5 makes the equation true.